Back on the body for the weather, so boys, happy boy, you in.
I be coming soon, but they rush me, I be down and I like making money when you're mamu, I'm getting money.
Good day, viewers all over the world. My name is Engineer Yemi Okweshade. We are here today for another STEM communication. But today we are looking at a preparatory communication, post-UTME tutorials. Okay, post-UTME tutorials in STEM, which comprises of maths, chemistry, physics, and biology. So in this communication, we shall be combining content from those STEM field or subjects. And you need to know that this is more relevant for students in Nigeria, and of course it could be applicable for people going for similar examination for admission. Now, the essence of post-UTME is that an examination has been conducted by JAM as an examining body for people that want to get entrance into the university. And then each university have their own standard also. They want to find out if the students that is seeking admission into their university is actually having the basic information, the basic knowledge for that kind of admission. So for that reason, they tend to conduct another test which focuses on the foundation, the basis. And so our focus here in this review exercise or communication shall be in touching those aspects that are of interest to the various universities in the country. So to make our work very easy and for us to have a better focus, I am having volume 1 of that expository today, volume 1. And our coverage have been itemized. We are going to look at cells and battery, electrical load and effect, reactance, resistance, impedance, mole concept, factorization problems, oxidation number, relative atomic mass of isotope, how to compute it, empirical formula, molecular formula, vapor density, molecular structure. We want to see the connectivity, matter and state. This aspect we are looking at the heat response, how different state of matter respond to heat, change of solid of formula. We'll quickly look at that. Ions, isoelectronics and electronic configuration and their implications. Then we'll try to look at radioactive particles and their nature, including some properties that they exhibit. Now, this communication is based on an understanding of what university like basing their question on from year to year. They focus on the foundation. Every topic in STEM has foundation, has basis. So they are more interested because it is in the foundation that there is a build up in the content expository for every topic in STEM. So at that level, they are much more interested. Do you have the basis? Do you have the foundation? Let's go and explain that. Now, we're looking at cell and battery. I'm not talking about biological cell now. I'm talking about electrical cell and battery. Now, a cell is symbolized as this. Okay? The shorter one is the negative charge of the cell, and the longer one is the positive terminal. So a cell has two terminals. Okay, the usual cell that we relate with. Okay, it has two terminals, the negative terminal and the positive terminal. So the longer one reflects negative, shows positive terminal. The shorter one is negative terminal. That is a cell. Okay. Now, if you have two or more cells gives a battery. So I can have this one cell, another cell, another cell, another cell. How many cells is this? 4. I have 4 cells. If you look at this, it is connected in series. positive, negative, positive, negative, positive, negative. Now, if I know the value of each one of them, the total EMF, every cell has a voltage content called EMF. EMF, electromotive force, is the voltage content in terms of charge content in a battery or cell when it has not been converted, when it has not been connected to any load. If you have a battery that has not been connected to any load, when I say load, we are referring to the bulb, the appliances, the TV, the radio, every electrical appliance that depend on electricity to function are called loads, electrical load. We'll soon come there now. So the voltage content, when it is not connected to any load, is called electromotive force. Okay, then the opposite of that is potential difference. That is when it has been connected. The voltage across load becomes the potential difference. So the total electromotive force will be the sum. Maybe it is E1 plus E2 plus E3 plus E4. Now there's another way I can connect two cells that you need to be mindful of. If I connect it this way, look at this. I connect positive and negative, that's one cell. And I connect another one negative and positive like this. I turn it the other way around. You can see that two negatives are following each other. Then this is parallel connection. So it means that this one, you're going to subtract. Okay? So if this is 7 volts and this is 5 volts, the net voltage, when I say net, total, equivalent, or overall, the overall voltage, it starts with the subtraction. It starts with 7 minus 5 volts, which is 2 volts. Take note of that. I can also have it this way. Look at it. I can have it this way. I can have the positive being turned to positive. Okay, and then I have the negative like this. Do you see that? Okay, so it's also positive following positive. You have to subtract also. Okay, but if you have it this way, positive terminal, negative terminal, another positive terminal and negative terminal, the total EMF or the effective EMF is addition. You add E1 plus E2. This one, because positive is following positive, the total EMF will be E1 minus E2 or E2 minus E1, depending on which one is greater. I believe you understand that. Now there is a what you call lead battery accumulator. Lead battery accumulator. Lead. That is the car battery. The car battery. The technical name is lead. This can simply call it lead accumulator. Okay, lead accumulator. The battery that powers a vehicle or a motor to work, to move. Okay, it's called lead accumulator. Okay, now it has 6 cells, and each of the cell is 2 volts. So 2 times 6, that will be 12 volts. Take note of this. The technical name for a car battery is lead accumulator. Okay, the electrolyte is H2SO4, sulfuric acid. That is the liquid electrical conductor that is inside it. Okay, and then the electrodes are made of lead material. So that's what they call it, lead accumulator. But now you want to ask, does this 12 volt battery go for all kinds of vehicles? Yeah, that is why there is what they call capacity. Every battery has capacity expressed in amp currents. A for ampere, H for hour, amp currents. Okay, so which is written as coulomb. Okay, that's the unit for expressing electrical charge or quantity of electricity. Take note of that. The unit for expressing electrical charge or quantity of electricity. Now, where am I going? The engine capacity of a vehicle determines the type of battery you put there. Though they will be reading 12 volts, but the capacity is different. So you can have a vehicle for a lorry, for a truck, for a small car, for a heavy engine vehicle are different. So they normally have something like 80 amp hour, 60 amp hour. So if you want to go to the market to go and buy battery for your vehicle, you have to know the required capacity of battery for your vehicle. Though it will be 12 volt, but is it that of the 60 ampere or 80 ampere? It will be indicated. Now don't forget the quantity of electricity, which is the charge. Q is current times time. Okay, if you check your phone battery, they will express it in milliamps hour. Okay, in milliamps hour, they will say 3000 milliamps hour. Check your phone battery. Sometimes they will say 5000 milliamps. It's just telling you the capacity. You know, when you are trying to select your phone, Android phone, WhatsApp for, okay, you want to know the capacity of the battery first, because that determines the hour it can last once it is fully charged. Okay, so that charge content is current times time. Is that clear? That is current times time. We will still look at something related to this. Now let me tell you one important thing before I leave this particular one. Now, the voltage required to kick a vehicle to function, to make a vehicle to move, is not 12,000. It's actually something around 10,000 volts. See that? Take note of this. What you put inside your vehicle is 12 volts. But what the vehicle needs, when you put your key in the initial steering side of the vehicle, is 10,000 volts. How then do you have 12,000 being converted to 10,000 volts? At the ignition system, at the steering area of the vehicle, there is a coil called induction coil. Induction coil. Take note of this. Induction coil. This induction coil, okay, has the primary and secondary coil. It has two sides, just like the transformer has primary side and secondary side. Induction coil also has, okay. Now the battery is connected to the primary side, and the secondary side is the output, is the one that really powers the vehicle. So that the number of coil at the secondary side is more than the number of coil or windings at the primary side. And so by the time you put your key in the ignition system, a 12 volt battery, a very small 12 volt voltage is converted to 10,000 volts. It is after that happens that your vehicle will move or respond. So take note of that. I believe you have gained a lot of facts and a lot of points around this. So many things I've said about this one. So we move away from this as foundation. Don't forget, they are more interested in foundation, and that is what we are trying to do. Let's go to the second point, electrical load. Now when we talk about electrical load, okay, we are talking about those things that respond or that changes to current flow, or that resist, that tend to resist. The response is in terms of resistance to current flow. Now, electrical load in this context has to do with every electrical appliances. Every gadget, every appliances that depend on current flow, electricity supply, are called electrical loads. Starting from the common bulb that lightens our rooms, okay, that lightens our environment. It's a load, and it showcases different resistance. You can compare the resistance that will be showcased by a bulb to a pressing iron, or to that of freezer or refrigerator or air conditioner. Do you understand that? So all those things that function, that rely on electricity to function, are called electrical load. Now, fundamentally, there are some elements inside these materials, these gadgets, that are really the load, that contribute to the load. We have three of them. We have resistance, we have resistors, we have capacitor C, and we have inductor L. This is resistor, we have capacitor, and we have inductor. Each of these respond differently to current flow. Okay, these are their symbol. Okay, each of these, we talk about resistance of resistor, capacitance of capacitor, and inductance of inductor. The unit of this is ohm. This one is in farad. Okay, farad, that is F. This one is ohm. This one is in Henry, capital letter H. That is the unit. And the symbol is this. For resistor, you can either symbolize it like this, or sometimes you do like this to symbolize it. So when you see this, you know that okay, you are referring to resistor of resistance of resistor. For capacitor, it is two plates of equal height. Take note, two plates of equal height. One positive charge, the other one negative charge. Then inductor is like a coil, like electric coil, like this boiling coil, like a coil. Okay, like a solenoid, a coil, or it's like a coil, or something that looks like a solenoid. Okay, or armature. Okay, armature. Okay, they are when you take an electrical conductor like copper wire and you wind it into a coil, then what you have is inductor. So this one has some kind of behavior display with resistors in terms of connectivity, which we are going to look at very soon. Now, what is very important? There are so many things I've told you here: the symbol, the symbolization, the name, the units. Okay. Now, what is the effect? Because that is it, electrical load and effect. Which effect did they display? Okay, this one display heating effect. Take note of that. That is where you're able to get from your pressing iron the heat to iron your plot. Capacitor, this one causes electric effect. Electric field effect. It creates electric field effect, and it is used in storing electric charges. Take note of that. Capacitor is used in storing electric charges, and that is the secret behind most of this rechargeable lantern. Okay, you know, when it has run down, you plug it to NEPA source, it charges. After NEPA might have taken the light, you light your rechargeable lantern. Why? Because it contains capacitor that is used to store electric charges. Okay, now inductor, what effect? This one called magnetic field effect. It causes magnetic field effect. That is inductor. Okay, and so meaning it can store magnetic what? Magnetic field. Okay, now in terms of connection, now let's look at the connectivity of this and how to find the total load when we have more than one of these components. For example, resistor now, it may be connected in series and in parallel. Capacitor can also be connected in series. I have two capacitors of capacitance. This, you see it, and then can also be connected in parallel. Okay, then inductor can be connected also in series and can be connected in parallel also. Okay, now this is R1, R2, R1, R2, R1. I mean, this is C1, C2, C1, C2. This is L1, L2, L1, L2. Okay, connected in. So we have series connection and parallel. What do you mean by series connection? Series, when you intermittently means positive terminal with negative terminal. Okay, you have series. Parallel connection, that is when you separate the positive terminal of a gadget from the negative terminal. You separate them. You can see this. As the current is coming here, these are positive, is also positive. Then when it crosses over the load, it turns to negative. When it crosses over the load, it turns to negative. But if you look at this one is positive, negative, negative to this place. Then when it crosses, it turns to positive. You can see that this is positive, negative, positive, and then we interchange it that way. So that's the difference between series connection and parallel connection. So take note of that. Now, the next thing is, how do you find total resistance or total capacitance or total inductance? They either use the word total or effective or equivalent or net. They mean the same. It means total or aggregate. Now, for resistors in series, total resistance or effective resistance is addition. You add R1 plus R2. For parallel connection, resistors in parallel, the total resistance is the reciprocal of the sum of the reciprocal of each of the resistor. Okay, 1 over R2, depending on the number. Now, the same thing apply. I will leave this place now. I will jump to capacitor. Inductors in series is being computed the same way you compute resistors in series. So that means total inductance is also L1 plus L2. Meaning in series, in parallel, it will be 1 over LT equals to 1 over L1 plus 1 over L2. Now, but that of capacitor is different. Take note of that. That of capacitor is different. For capacitors, series connect, this one is series, this one is parallel. Okay? For capacitors, it is the opposite of what happened to resistors and inductors that happen in the combination here. For series, the total capacitance is the reciprocal of the sum of the individual capacitors. 1 over C1 plus 1 over C2. If it is more than that, you continue. Then for the parallel now, it will now be the opposite here. That will now add. Okay, that will be C1 plus what? C2. So we will be solving problems on this in subsequent edition. Take note of that. We will be solving problems on this. So but take note, volume 1 is very important. In volume 2 or any other volume, I may decide to solve problem to apply this. Okay, so we go to the third aspect: reactance, resistance, and impedance. Let's go to reactance, resistance, and impedance. Reactance is X, resistance is R, and impedance is Z. All these are resistance. They resist the flow of electric current. Now, this reactance, it means change in voltage over change in current. This resistance also means change in voltage over change in current according to Ohm's law. Impedance also means change in voltage over change in electric current. You know Ohm's law says that voltage is current times resistance. So for resistance, for reactance, this will turn to X. For impedance, this will turn to Z. Take note of that. Okay? So when you express capacitor, now this X now, which is reactance, is when you convert capacitor and inductor to ohms. No, the unit is from farad. This one is in farad. When you convert it to ohms, and this one is in Henry. When you convert it to ohms, then it turns to reactance. So we have two reactance: SC, capacitive reactance, SN, inductive reactance. When you convert ordinary inductor, so that the unit changes from Henry to ohm, you have inductive reactance. When you change ordinary capacitor, the unit from farad to ohm, then what it now becomes capacitive reactance. So there are formulas you use for this. Look at the formula. Let me start with inductive reactance. The formula is omega L. For capacitive reactance, it is the reciprocal of omega C, 1 over omega C. Now, what does this omega stand for? This omega This omega is 2 pi f. Frequency. We'll come back to that later. The frequency of flow of current, F. And you know inside frequency there is period. Frequency is 1 over period. Meaning that period, if you constantly see something in the formula, period is also 1 over free frequency. So this means that this formula can turn to 1 over 2 pi fc. Then this one is 2 pi fn. So take note of that. Okay, so we have capacitive reactance and we have inductive reactance. Now these three are mostly found in an AC circuit. AC alternating. You know the current flow in an AC is rising and falling, unlike that of DC that flow in one direction. DC, this is AC current graph, this is DC. This one is moving the straight line in one direction. We call it unidirectional. The flow in an AC, in a DC is a unidirectional, that means in one direction. But that of the AC is vibrational. Or you say it is sinusoidal. Or you say it is harmonic, meaning it moves like sine wave. So many names. AC is vibrational, sinusoidal, harmonic, it moves like sine wave. But that of DC is unidirectional. Okay? Now, what are the sources of voltage? What are the sources of voltage that give us AC? Number one, from hydropower, hydroelectric power, from solar, from nuclear power, okay, from generator. Those are the sources of volt current that rises and falling, that flow like AC. But that of the DC are the common cell or the common battery, like the car battery or the cell in your phone and the other gadgets like that. Okay, so the voltage capacity for cell and battery, which is in DC, are usually very low. Okay, but that of the AC, the voltage and current capacity is very high, and this one can be very dangerous for human existence. So it means that reactances are all in opposition to current flow, the opposed current flow, and they are only expressed in ohms once it exists as reactance, resistance, and impedance. We will look more about that in due course under this. So those are some of the foundational stuff you also need to understand here in this context. Now, I want to go to another important area. Okay, we'll go into another important area, which is mole concept. Mole concept. This is in chemistry. Mole concepts. You know that one of the fundamental units, one of the fundamental basic units in science, let's say quantity now, is amount of substance, which is expressed in mole. And sometimes when substances react together, they do so in quantifiable mole ratio. Okay, in quantifiable mole ratio. And that mole, sometimes you will be required to estimate it either in terms of mass, in gram, or in terms of volume, in dm cube, or in terms of particles, numbers of particles. Okay? Number of particles. Now, particles in science, in chemistry, could be molecules, could be ions, and of course, ions can either be cations or anions. It could also be atoms. It could be other particles, like electron, like protons, like neutron. Take note of that. Anything that is particulate, okay, are under this. So it means that there are ways in which mole quantification is being connected to physical quantities. So this mole is in this context symbolized as n. So the first formula is that if I want to know the mole of a particular substance that participates in a chemical reaction, I can say that mole n is mass over molar mass. It is also, in terms of volume, it is volume over molar volume. Now, all gases have the same molar volume. All gases, and that is 22.4 dm cube. Take note of that. All gases. Okay, whereas the molar mass of every substance is different. For example, sodium chloride. The molar mass of sodium chloride, you have to look at the molar mass, the mass number for sodium, which is 23, plus the molar mass of chlorine, which is 35.5. They add it together. That will be the molar mass of sodium chloride. For sodium carbonate, I want to calculate the molar mass for sodium carbonate. It's different from the molar mass of sodium chloride. But the molar volume of all gases, be it carbon dioxide, carbon monoxide, sulfur 4-oxide, and so on, they have the same molar volume at STP, standard temperature and pressure. Now, if I want to calculate the molar mass of sodium carbonate, how many atoms of sodium do we have there? 2. So that means that will be 2 times 1 molar mass of sodium, 2 times 23, plus carbon, 1 carbon. Carbon is 12, 1 times 12, 12. Plus, I have 3 atoms of oxygen here. The molar mass of 1 atom of oxygen is 16 times 3. That will be 16 times 3. 16 times 3. Altogether will give me the molar mass of sodium carbonate. I'm sure you are familiar with that. Don't forget that this is a revisional class. This is not a teaching class. I'm not teaching you. I'm reviewing what you ought to have learned over the years from GSS 3 to SS 3 in science. So this is another formula. Then also, we can also have mole being equals to, in terms of particle, number of particles over Avogadro constant. Avogadro constant, Na, or Avogadro number. This one is a constant. Just like molar volume is a constant, it's also a constant. We will always give it to you. So these are the formula that I use to compute the amount of substance that participates in the chemical reaction. There's another one that I want to include here. Look here. Mole can also be concentration of a substance. Concentration, okay, in mole per dm cube times the volume. Let me clean this. Times the volume of that substance that participated divided by 1,000. Okay, this one is in dm cube. Okay, this one is also in dm. So the concentration here, the mole here, N, is also concentration in units of mole per dm cube times the volume of that substance divided by what? 1,000. The fourth method, or the fifth method now, has to do with the analytical method, the one that is based on balanced chemical equation. We will definitely get there and solve problem on that. So you need to be familiar with this. Let me just take an example of this, even though we are still going to solve some problems in subsequent edition. For example, now let's say I ask you to calculate the amount of molecules in 2.7 gram of aluminium. Amount of molecules in 2.7 gram of aluminium, for example. Now, if you look at this, molecules, amount of molecules is a particle. That is a particle. So it means we need this formula, N equals to number of particles over Avogadro number. Again, they gave you the mass of aluminium, 2.7 gram. It means that we also need to connect mass over molar mass of aluminium. So the two of them are mole. So if this is equal to this, that means this one is also equal to this. So you come up with this formula here. Hello, NP over NA being equals to M over M molar mass. Do you see that? Did you see that? Okay. So this gives us, so we are looking for this number of particles. That means in this case number of molecules. That is X. Okay. The Avogadro number is 6.02 times 10 raised to power, I think is it 19 now? 19. Okay, I'm not very sure of that now. So it's a constant. They will give it to you. Okay, mole per dm cube. Okay, then equals to, is it down minus 19 or 19 or so? I'll confirm, please. Just take note of that. It's a constant. They'll give it to you. Equals to what? Mass. What is the mass given to that? I want to convert to molecules. 2.7. Now the question is, what is the molar mass of aluminium? If you check the periodic table, they will also give you this also. The molar mass, the mass number for aluminium is 27. So divided by 27. So you cross multiply to get your X. This times this equals to this times this. Then you calculate it. So we'll solve more problem on that over time. Okay, now let's go to another aspect. Now, look at this. Factorization now. Factorization. Factorization. Now, these are fundamental topics in mathematics. So, the university want to know whether you can handle simple factorization problems. So, we are looking at factorization problem part 1. Part 1. Okay? For example, let's say I give you the total surface area of a cone, which is pi Rn plus pi R squared. This is a simple equation. I can ask you to factorize this. What is the common factor here? What can you see here that you can bring out here? Pi, 1R, 2R, so I can bring out pi R. Okay? Into, use this to cancel this. I have L left. Plus, use this to cancel this. It will remain 1R. Stuff like this. Okay? Fall under factorization problem 1. Okay? Number 2 is the one that involves what I call difference of two squared method. There are some factorization problem that is associated with difference of two squared method. Now, let's look at the interpretation of that. 2 squared, two things are being squared, a squared and b squared, for example. Difference means there's some minus in between them. That's difference. Now, the law of factorization that go with this is that if you have two things being squared like this, okay, then these factors is this: a minus b into a plus b. A minus b into a plus what? Into a plus b. Okay? You can verify that if you have 7 squared minus 5 squared. Okay? Let's confirm if this is valid. 7 squared, you know that is 49. 5 squared, 5 times 5, that's 25. So 49 minus 25, that gives us 24. Okay? Now, it gives us 24. Now, let's try to apply this method, which says if you have two things being squared, separated by difference, it will be 7 minus 5 into 7 plus 5. Let's see whether we'll get the same answer. 7 minus 5 is 2. 7 plus 5 is 12. You can see that 2 times 12 gives us 24. That means this is valid. Now, let's take some example of this because that one is more, this one is more important than the first one. Look at this. Let's assume that I have to factorize this completely. Factorize 16b raised to power 4. Okay, let me start from the simple one first. Let's say I say to factorize 1 minus 81b squared, for example. Now, the question is that we have two different terms. Can we express this one in terms of squared? Yes. 1 can be expressed to any exponent. 1 times 1 is 1. So this one is 1 squared. It's still 1. Minus this one, 81 is 9 squared dot b squared. Because these two are together. So and they have the same exponent now. So you write it like this: 1 minus, you pick 1 9, You pick 1b, then you squared it, okay? Then this give you, then this one is already squared. Then now, we now have two things being squared now. You cannot apply the formula. It will now be 1 minus 9b into 1 plus 9b. Is that clear? Alright, now let's take another example. Sometimes they may give you something very funny like, I may say, factorize 5m minus 125 m raised to power 3. Now, sometimes, if you look at this is not squared. Because we are looking at difference of two squared, two things from the square, and this one we are already having m raised to power 3. This 125 is 5 raised to power 3, 5 times 5 times 5. But here, if you look at this side, there is a common factor here. 5 can go here, 5 can go here. M can go here, M can go here. So we bring out those factors first. Is that clear? So this gives you 5m into, now, this cancel this. What you have left is 1 minus, use this one to divide this. 5 in 125, that is 25. M in M cube, that will be, it will remain M squared. Okay? Now look at the one inside the bracket. It's like the one we saw that preceded this now. This is 5m into, this one can be written as 1 squared. This 25 can be squared just like this m is squared. So that means you pick 1 5. Then you pick 1m, then you square this. Is that clear? Because 5 squared is 25. Then m squared is m squared. Now, inside this bracket now, we can now apply difference of two square method. This will be 5m into 1 minus 5m. Then into 1 plus 5m. One will be positive, one will be negative. You can decide to make this one positive first and make one. Just make sure that one is positive and one is negative. And that is the answer. Okay, so this is the factor to this problem. Now, again, I want to solve another problem on this. Okay, we are still looking at part 1 of this factorization problem. Okay, look at this. Let's say I ask to factorize this. Factorize 16q raised to the power 4 minus 81d raised to the power 4. This also conforms to difference of two squared method. You see, when you see exponents that you can get 2 out of it, because out of 4 I can get 2 out of it. Out of 4 I can get 2. Then this 16, if you look at it, I can express 16 also to the power of 4. That is 2 raised to the power 4. 81 to the power of 4. That is 3 raised to the power 4. 3 times 3 times 3 times 2 give me 81. You know, 81 is 9 times 9. And I can get 2 3 from 9. 16 is 4 times 4. I can get 2. I can get 2 of. I can get 2 from 4. Is that clear? Okay. That, yes. So it means that this one, you have to first of all say 16 is 2 raised to the power 4 dot q raised to the power 4 minus 81 is 3 raised to the power 4 dot what is this, d raised to the power 4. Now both terms now are having exponent of 4. That means I can say I can pick 2, I can pick 1q raised to the power of what, 4 minus this one I can pick 1 3, I can pick 1g raised to the power of what, 4. Now look at this. Don't forget that our method is difference of two squared method. So it means that I have to look for a way of bringing out something squared, not something 4 that is there. So if you look at this can be 2q raised to the power 2 bracket raised to the power 2. 2 times 2 is 4. Minus, we do the same thing here. This will be 3d in bracket raised to the power 2. Everything bracket raised to the power 2. Exponent multiply exponent. 2 times 2 is still 4. Now let's come here. Let's see what is happening here. Now I know how I do it now. Because for you to apply this difference of two square method, two things must be squared. So they are squared now, right? So we now have this. It will now be 2q squared minus 3d squared in brackets. Then I also have 2q squared plus 3d squared in brackets. That okay? Now, if you look at this one, you can still apply difference of two square method because there's a difference and two things are still being squared. So, but this one, there's nothing you can do to this one. Okay? This one is already like this. Okay? So it means that this one, I can say 2q, please the camera here, 2q minus 3d. I can have 2q plus 3d. Okay? Then this one I can open it up because this one is not difference, it's plus. So what is 2 squared? That is 4. What is q squared? That is q squared. Plus what is 3 squared? 3 times 3, 9. What is d squared? That is d raised to power 2. So the factors are 3. 1, 2, 3 are the factors of this. So with this, we have come to the section 1 of volume 001, which is we have looked at a review of cell and battery, electrical load and effect, reactance, resistance and impedance, mole concepts. Then we looked at factorization. So we'll come back in another video for the section 2 of this volume 1. So till we upload that video for you, try to go through what you have said. Look at it. I expected you to have penned down so many points, so many facts. Try to articulate that. You can imagine how many questions that can come out from what you have just reviewed. 1, 2, 3, 4, 5. I can set so many questions from there that are foundational, that your university of choice will be interested to test you on. So till another time, you have a good time.
Bapa la balik ke depan, so boys happy boy you